Hi, today we are gonna take a look at this stall warning computer. I bought that thing a long time ago, 4 or 5 years. I did the complete reverse engineering of that unit in 2022. I think it can be interesting to take a look inside. And after that I will try to connect this angle of attack sensor, okay, to this unit, and to connect the output of this stall warning computer to an angle of attack indicator. This one, for example, I have studied in my last video. Okay, so by the way, this thing was manufactured in 1997 by Rosemont Aerospace Incorporated. You can see the part number. All I found is that it was used in a small aircraft. Okay, inside we have 5 electronic boards. Okay, so we can see here a filter. So this line corresponds to the 28 volts of power supply. Okay, so let's start with the first board. As I said, I have already done the reverse engineering, so I know exactly what is the purpose of this board. This board is actually a 400 Hz sine generator in order to drive the synchro of the angle of attack sensor, which is here. So this permits to supply the rotor of that synchro here. So this is actually a VIN oscillator. Okay, so we can see the schematic of this board. So we can see here the oscillator. Okay, so we can recognize here the two RC networks for the bridge. And we have here the amplifier. Okay, so the output of this amplifier is connected to the input here. And the output here is connected to the input of the amplifier. So the gain is controlled. So the oscillation is controlled by the rectification of this voltage. So this permits to have here a single wave rectifying. So the mean value is calculated. It corresponds to the RMS voltage at the output here multiplied by square root of 2 divided by pi. Okay, we can see that we have a gain of -1 here. So this permits to have a positive DC current flowing through these resistors here. And here we have an integrator. Okay, so therefore we have here a virtual ground. The voltage is 0. Okay, and this current is compensated by another negative current, okay, which is given by this reference diode here, which gives a reference voltage of -6.9 volts. And this resistor. Okay, so at the end you can calculate, because we have of course a null DC current flowing through this capacitor. So this permits to say that this current is the same than this one. So this permits to calculate the output RMS voltage here, which is after calculation 8.6 volts RMS. So this corresponds to a voltage of 24.5 volts peak to peak. So this is the power op-amp. There is a current limit using these two resistors here. So this part is very expensive, close to 300 euros, I think. Okay, the power op-amp is this one here. And we have a detection of the current flowing through the rotor of that synchro. Okay, so the synchro is connected between the output here, terminal A, and terminal B here. Okay, so there is a current sense resistor of 10 ohms. So the current is detected. So this is a fault signal. And on that board there is also a voltage follower. So this is the angle of attack output. Okay, so this is the first board, which permits to drive the synchro of the angle of attack sensor. Okay, so we have here another board. Okay, we can see that there is a conformal coating, so it is the case for all boards. So there is here a TVS diode. So I don't remember the function of this board. So this board is a 2339. Okay, so we can see from the reverse engineering of this complete unit. So the angle of attack sensor is here. Okay, so we have seen on the first board, which is this one, the 400 Hz sine generator here, which permits to drive the rotor of the synchro here. and we can see here the current detection. The stator of the synchro is fed to this differential amplifier, and there is a synchronous detection which permits to convert the AC voltage into a DC voltage after low pass filter. Okay, so there is a comparator which permits to have a square wave at the same frequency, and at the output here we have an image of the angle of attack, and we can select different gains. And here this is the second board, so this permits to activate a kind of test. There is a relay here. Okay, so this is the output of the angle of attack. We have already seen this voltage follower, okay, on the first board, and we can see that we can select between the angle of attack and a ramp which is given by this board, 2339. There is also a detection of a fault. The first fault corresponds to an open synchro here. Okay, so this is the function of this board. It's a kind of error board. Okay, so this is the board 2335. Okay, so there is a quadro pump and a few transistors and another LM158. Okay, so the board 2335 permits to convert the output of the synchro here, which is an AC voltage, into a DC voltage. This is the front-end board for the angle of attack sensor. So this is a differential amplifier connected to the synchro here. There is a gain of minus 3.3 when this transistor is on. Otherwise, when this transistor is off and this one is on, and there is a gain of minus 1 here. Okay, and the output here is connected to this resistor, which permits to have a gain of minus 3.3. So we have a gain of plus 3.3. So this permits to alternate between a gain of minus 3.3 and a gain of plus 3.3. We can see we have a comparator which permits to invert the square wave, and we have here another comparator which permits to generate a square wave at 400 Hz. Okay, so the input here is connected to the output of the generator. At this output we have a full wave rectifying. This voltage is filtered using this strong low pass filter here, and at the output there is a DC voltage, and this output is fed to this amplifier. The gain can be selected using these two inputs here, E and D. Anyway, there is an adjustment here of the gain and another adjustment of the offset. Okay, and the signal is fed to the voltage follower we have already seen. For the test, I will connect the two terminals of the synchro together, like in this diagram for a Boeing 727. So you can see we have the AC voltage on that point, and the second point is connected in normal mode to the AC voltage also. In test mode, there is a capacitor in series, so this permits to have a phase shift and to change the direction of rotation of this indicator here. The third terminal here is connected to ground. We can see here in yellow and green the two outputs of the synchro. The blue curve shows the difference between these two signals here. For 0 angle of attack, these two signals are identical. The difference is null. Otherwise, we can see that the difference increases depending on the angle of attack here. Okay, so there is a phase reversal for positive angle of attack. The difference is proportional to the sign of the angle of attack. The result is here from minus 60 degrees to plus 60 degrees. We can see the difference of these two AC voltages. So this is RMS voltage, okay, negative when there is a phase reversal. So there is a small offset at 0. It is not totally 0, but 200 millivolts. We can see on the screen the output voltage here. So we can see that we have an RMS voltage of 8.4 volts instead of 8.6 I have calculated, but anyway this voltage is adjustable by this trimmer, and the frequency is 494 Hz. For the test I have connected this sensor to the stall warning computer. I have connected also this angle of attack indicator to the output of this computer. I have described this indicator in one of my first videos. It was episode 27. I have connected also this indicator box, and there is here a switch which permits to activate the auto test. The green indicator here corresponds to normal mode, and this indicator turns off when the auto test is activated. Okay, so the indicator is connected from the collector of this transistor to 28 volts power supply. The angle of attack auto test is activated by pulling down this line here, G. Okay, so G is connected to this switch, which is connected to ground. Okay, so we can see that if we have a low level on that point and there is a high level on that point, okay, so this permits to activate the switch and to deactivate this one thanks to this inverted gate here. And so when you have something like that, especially using CMOS logic, it is better to connect one input to the power supply and not connect it together. If you connect together, you can have a glitch at the output. This output corresponds to a ramp which is given by this capacitor and this current source. There is a 555 which permits to activate the sequence. This indicator was not fully compatible with this stall warning computer. So I had to modify some values here. On that point there is a null voltage for a null angle of attack, but here we have a gain and there is an offset created by these two resistors, and we have a gain adjustment. Okay, so this positive voltage creates at the output a negative bias, and we can add also a positive bias using this trimmer. The problem is that an adjustment of the gain has an effect on the offset here, because this offset is amplified also. I don't understand why they didn't use here a bipolar adjustment by connecting this point to a negative voltage. So I have removed this resistor. In that case, we don't have a modification of the bias when there is an adjustment of the gain. Okay, so for this indicator, we need approximately a voltage of 4.8 volts for 0 and 10 volts for 30 degrees here. So I have added also a resistor here in series in order to reduce the gain because the sensitivity was too high. These two lines are not used. It permits to increase the gain. Okay, so we have here two p-channel JFETs. Okay, so we can see we have two resistors which permit to have a positive gate to source voltage here. So therefore these two transistors are off by default, and if you connect one or these two lines to ground, this permits to turn on one or these two transistors, and therefore the gain is increased because one or both resistors are in parallel to this one. Okay, so this one permits to set the minimum gain, and the gain can be increased here. Okay, so we can see also the output buffer. There is a protective resistor here of 1.8 kilo ohms. This resistor permits to protect this op-amp against short circuit and surge and so on. So the problem is that the output voltage depends on the load. So there is a better approach for that. In that case, the feedback is connected to the output. Okay, so there is an automatic compensation here. Okay, and you can add also a capacitor for stability. And in that case, you have a protection because you have these two resistors. Okay, so if you have a load, this will increase the output of this op-amp. But anyway, you have a compensation of the voltage drop here. And at the same time, you have a compensation of the bias current of this op-amp using this resistor. This is not the case here. Okay, so the oscilloscope here is connected to the output. which is the input of the angle of attack indicator here. This lamp is activated in normal mode and is off in test mode. This lamp corresponds to the critical angle of attack. Okay, so it is connected between this output, which is actually an open collector here, and the power supply. Okay, so there is here an adjustment which permits to set the critical angle of attack. So there is here a current source which permits probably to activate the stick shaker, but I'm not sure. There is another complex circuit here which depends also on the flaps. Okay, it corresponds to this schematic. It is not very obvious. The third lamp here corresponds to a fault. Okay, so now I am going to turn on the power supply. Okay, so the test mode is activated here. Okay, in test mode there is first a discharge of the angle of attack down to 0 and a linear increase of the voltage up to the maximum, approximately 10 volts. Okay, so this permits to test the indicator and the limits also. We can see that we are above the critical angle of attack, and also we are above the allowable limit of the angle of attack. I will return to normal mode. Okay. So the normal angle of attack is when the van is like that. Okay. So here we have the critical angle of attack. So it is generally between 15 and 20 degrees. I have adjusted this angle of attack at 18 degrees or something like that. Okay. And here we are outside the limits. There is an error. And it is the case for a negative angle of attack. Okay, so I have adjusted the gain and the bias in order to have exactly 0 indication for 0 and 20 for 20. And that's all for this stall warning computer. Thank you for watching and see you next time for another one. Bye bye.